Greetings, explorers of the night sky. Are you ready to embark on a captivating journey to unravel the mystery behind the mesmerizing Aurora Borealis, also known as the Northern Lights? Imagine a celestial dance of light, shimmering curtains of green, purple, and red, painting the canvas of the night sky. This breathtaking spectacle has held humanity in its thrall for centuries, inspiring countless myths, legends, and scientific inquiries. But what causes these vibrant displays? What cosmic forces are at play behind this spectacle? Today, we embark on a journey of discovery, delving into the science behind the Aurora Borealis. We'll explore the invisible embrace of Earth's magnetic field, the sun's fiery dance, and the celestial collision that results in this spectacular light show. So buckle up, keep your eyes on the heavens, and prepare to witness the dance of lights in a whole new light. Today, we'll delve into the science behind the Aurora Borealis, exploring Earth's magnetic field, the sun's fiery dance, and how these forces collide to create this spectacular light show. So what's the first piece of this celestial puzzle? It's the Earth's invisible shield, our magnetic field. Imagine, if you will, a colossal magnet, just like the tiny ones on your fridge, but on a planetary scale. This magnet stretches a force field from the South Pole to the North Pole, forming a protective bubble around our planet. This bubble, our magnetic field, shields us from the majority of the sun's relentless solar wind, a constant stream of charged particles that could strip away our atmosphere if given the chance. But what creates this invisible shield? The answer lies deep within our planet, in the core. The Earth's core is a swirling cauldron of molten iron and nickel, heated to unimaginable temperatures. As the molten metals in the outer core move and churn, they create electric currents. These currents, in turn, generate our planet's magnetic field, a symphony of forces playing out beneath our feet. The strength of our magnetic field isn't constant, though. It fluctuates, changing and shifting with the movements in the Earth's core. Despite these fluctuations, our magnetic field has been a reliable guardian, standing between us and the solar wind for billions of years. It's like a silent, invisible superhero, constantly saving the day without us even realizing it. Our magnetic field doesn't just protect us, though. It also interacts with the solar wind, creating some of the most awe-inspiring sights in our natural world. When the charged particles in the solar wind manage to sneak past our magnetic field and collide with the atoms and molecules in our atmosphere, they create the spectacular displays of light we know as the auroras. This magnetic shield, generated by our planet's core, is our first line of defense against the sun's powerful solar wind. It's the Earth's magnetic embrace that not only protects us, but also sets the stage for the celestial dance of the Aurora Borealis. Now, let's turn our gaze to the source of this solar wind, our very own star, the sun. A colossal orb of energy, the sun is a blazing ball of hot plasma, continually emitting light and charged particles. This ceaseless ejection of energy is what we refer to as the solar wind. Imagine the sun, not as a solid object, but a swirling, churning sphere of plasma, held together by its own gravitational pull. This plasma is a superheated state of matter, a cocktail of ions and electrons, seething in a ceaseless, fiery dance. Among the myriad of celestial ballets, the sun's dance is both beautiful and powerful. It's a dance that can be gentle, with a steady rhythm of solar wind, but it can also be wild and unpredictable. And it's during these moments of heightened activity that we witness some of the sun's most dramatic performances: solar flares and coronal mass ejections. These are not just spectacular to observe, but they have a significant role in the narrative of our northern lights. Think of a solar flare as an intense burst of radiation, a sudden flash of increased brightness. Often following these flares, the sun can also eject a massive bubble of plasma, a coronal mass ejection. Propelled by the sun's magnetic field, these charged particles rocket into space at high speeds. But what happens when these charged particles, these dancers if you will, hurtle towards Earth? They encounter our planet's magnetic field, our protective shield. While most particles are deflected, some are funneled towards the poles, where the field lines converge. And it's here, in the upper atmosphere, that our solar dancers meet Earth's atmospheric molecules. The energy from the charged particles excites these molecules, and when they return to their normal state, they emit light. This light, seen in the form of glowing curtains of color, is the aurora borealis. These solar storms, releasing bursts of charged particles, set the stage for the celestial dance that creates the aurora borealis. It's a performance that spans the astronomical stage, from the fiery heart of our sun to the cold reaches of our planet's poles, creating a spectacle that leaves us mere spectators in awe of the universe's grandeur. With Earth's magnetic field acting as a guide, these charged particles from the sun embark on a journey towards our planet's poles. Let's imagine this scenario as a cosmic highway where these particles are the travelers, and Earth's magnetic field is the road they traverse. Our planet's magnetic field is a fascinating phenomenon. It's like an invisible force field that extends thousands of miles into space, protecting us from the relentless solar wind. This field is strongest at the poles, where the lines of magnetic force converge. As if drawn by a celestial magnet, some of these energetic particles from the sun are funneled towards these polar regions. But what happens when these charged particles make their way into our atmosphere? Well, that's when the real magic begins. These particles, bursting with energy from their fiery solar origin, collide with atoms and molecules in our atmosphere. This collision is more than just a simple bump in the cosmic road. It's a transfer of energy, causing these atoms and molecules to become excited, much like how you might feel a rush of adrenaline when riding a roller coaster. Now, atoms and molecules don't like to stay in this excited state. They prefer to return to their normal or ground state. But to do so, they have to release the extra energy they gained from the collision. And guess how they do it? They emit light. This is the very light that paints our night sky with the dazzling colors of the aurora borealis. Imagine it like this. Each atom or molecule in our atmosphere is an artist. The charged particle from the sun is like a brush dipped in energy, and when they collide, the atom uses this energy to paint a stroke of light across the canvas of the night sky. Each stroke is a tiny part of the larger masterpiece we know as the Northern Lights. But did you know that not all atoms and molecules paint with the same color? The color of the light depends on the type of atom or molecule involved in the collision and how high up in the atmosphere the collision takes place. The most common color, a brilliant green, is produced by oxygen molecules about 60 miles above the Earth. Higher altitude oxygen can also produce a rare, all-red aurora, while nitrogen produces blue or purplish red aurora. This celestial collision is not just a random event. It's a dance of charged particles and atmospheric gases, of energy and light, of magnetism and color. It's a dance that has been going on for billions of years, choreographed by the laws of physics and performed on the grandest stage of all, our universe. So the next time you look up at the night sky and marvel at the spectacle of the Northern Lights, remember the incredible journey of these charged particles and the elegant physics behind their dance of light and color. This remarkable collision of particles and atmospheric gases paints the night sky with a breathtaking array of colors. But what gives the aurora borealis its enchanting colors, you might ask? Well, the answer lies in the very air we breathe, the atmosphere. Our atmosphere is a cocktail of different gases, predominantly nitrogen and oxygen. When the charged particles from the solar wind collide with these gas molecules, they transfer some of their energy to them, causing the molecules to become excited. Now here's where the magic happens. As these excited molecules return to their normal state, they release the energy they received as light. The color of this light depends on the type of gas molecule involved in the interaction and the altitude at which the collision occurs. The most common color we see in the aurora borealis is a brilliant green. This green light is produced by oxygen molecules about 60 to 200 miles above Earth's surface. When these oxygen molecules are struck by charged particles, they emit a beautiful green light as they calm down from their excited state. But the aurora borealis isn't always just green. At higher altitudes, around 200 miles or so, oxygen can produce a rare red aurora. This happens when the particles collide with oxygen in a higher energy state than what causes the green light. And what about the blues and purples we sometimes see? These colors are thanks to nitrogen. When charged particles collide with nitrogen molecules, they can emit a blue or purplish light. Nitrogen can also contribute to the reds in an aurora, particularly at the lower edges of the lights. So each color of the aurora is not just a spectacle for our eyes, it's a unique signature of a particular gas molecule, dancing in harmony with the solar wind. Each hue tells a story of a cosmic collision, a story of energy transferred and released, a story of our atmosphere's silent guardians that turn a potential cosmic threat into a breathtaking light show. So each color of the aurora is a unique signature of a particular gas molecule, dancing in harmony with the solar wind. Now that we've unraveled the mystery of the Aurora Borealis, how can you experience this celestial spectacle for yourself? Well, the first step to witness this extraordinary cosmic ballet is to head towards the polar regions. Generally, the Aurora Borealis is best viewed in high-latitude regions such as Alaska, Canada, Iceland, and Scandinavia. The farther north you go, the greater your chances of catching this glorious show. However, merely being in the right location isn't enough. Timing is equally crucial. The best time to see the northern lights is typically during the winter months, from late September to late March. The long, dark nights provide the perfect canvas for these vibrant illuminations. The intensity of the aurora can vary greatly, and it's largely dependent on solar activity. During periods of high solar activity, the lights can be seen more frequently and are often more vibrant. So, it's a good idea to keep an eye on solar forecasts. But there's more to it than just solar activity and location. The weather plays a significant role too. Clear, dark skies are ideal for aurora viewing, so it's key to check the weather forecast. Furthermore, avoiding light pollution by steering clear of city lights can significantly enhance your viewing experience. Now, as for the gear you might need, a warm coat and a thermos of hot coffee are essential. It can get quite chilly while you're standing outside, waiting for the lights to appear. For those keen on capturing the spectacle, a camera with manual settings and a sturdy tripod can be your best companions. Remember, patience is a virtue when it comes to Aurora Borealis. The lights may not always show up when expected, and even when they do, they can be fleeting. But don't let this discourage you. The wait is well worth it when you finally see the sky come alive with a dance of colors. The mesmerizing dance of the Aurora Borealis awaits you. So why not venture out under the night sky and witness this enchanting spectacle for yourself?